You ever just stop and think about how fragile our existence feels? We're on this little blue marble, just whipping through the absolute emptiness of space. It feels like we're balanced on a knife's edge, right? Like one tiny nudge, one little mistake, and it's all over. But is that actually true? Let's dig into the real science behind our place in the cosmos.
I mean, this is the classic question, isn't it? It just feels so intuitive. A little closer, and we all turn to toast. A little farther away, and we're a planet-sized popsicle. It's this scary idea that we're stuck in this one perfect, tiny little sliver of space. But what if I told you that our orbit is way more resilient than that, and that the truth reveals a much, much deeper cosmic story?
Yeah, because the story of how Earth stays stable isn't just about being the right distance from the sun. Not at all. It's more like a cosmic dance, this incredibly intricate push and pull of forces that has shaped our planet, the length of our days, and our very existence over billions of years. So let's start to unravel this cosmic ballet.
Okay, so to get a handle on our stability, we first have to talk about our cosmic address. And you've probably heard of this before. It's called the Goldilocks zone. You know, the area around a star where things aren't too hot, not too cold, but just right.
So the fancy term for it is the habitable zone. And really, it's all defined by one thing, the potential for liquid water on the surface, which is, the one ingredient scientists agree is pretty essential for life. But here's the thing. Our sun's habitable zone is actually huge. It stretches from somewhere around the orbit of Venus all the way out past Mars. That's a pretty wide margin, which kind of suggests we're not on a razor's edge, at least not in the way we usually picture it.
And get this, Earth's distance from the sun already changes by a massive amount every single year. Our orbit isn't a perfect circle, it's an ellipse. So in January, we're about 147 million kilometers away. But in July, we're out to 152 million. That's a 5 million kilometer swing.
And here's the real mind-bender. That huge variation in distance has almost nothing to do with our seasons. If you're in the northern hemisphere, we're actually closest to the sun in the middle of winter. The real reason we have seasons is the 23.5-degree tilt of our planet's axis. So right away, we see that a simple change in distance isn't the catastrophe we imagine. There's a much bigger, more fundamental force running the show.
And that, of course, brings us to the master architect of the universe, gravity. It's the force that writes the rules of the road for everything, from an apple falling from a tree to entire galaxies orbiting each other.
This is the foundation, right? Isaac Newton laid this out way back in 1687. And put simply, it just means bigger things pull harder and things that are farther apart pull weaker. It's this beautiful, elegant law that perfectly described how the planets moved. But even for Newton himself, there was this deep, really unsettling mystery hiding right at the center of it all.
This is one of Newton's most famous quotes. See, he could describe gravity with absolute mathematical precision, but he refused to even guess what it was. The whole idea of action at a distance, one object magically pulling on another across empty space, was, and this is his own words, so great an absurdity that he just couldn't bring himself to speculate on how it worked. He knew what it did, but he had no idea why.
Newton's laws were completely revolutionary, but they treated gravity as a simple force between the dead center of two objects. And this simplified picture misses a subtle, yet totally world-shaping detail. A detail that reveals a powerful, hidden force at play.
We usually think of gravity as just a pull, but it's really more of a gradient, a field that gets weaker with distance. And that subtle difference from one side of an object to the other gives rise to this incredible secondary effect, tidal forces.
Think about the moon. It doesn't just pull on the center of the Earth. It pulls on every single part of our planet. Now, because the side of the Earth facing the moon is closer, it gets pulled a little bit harder. The far side, being farther away, gets pulled the weakest, and the center of the Earth gets pulled somewhere in the middle. So what's the result of this differential pull? Well, it literally stretches the Earth out. It creates a bulge of water on the side facing the moon, and, counterintuitively, it also creates a bulge on the side facing away from the moon because the solid Earth is being pulled away from the water on that far side. It's why we have 2 high tides every day.
So this is the key. A tidal force isn't really about lifting things up, it's about stretching them out. And this stretching doesn't just apply to our oceans. It happens to the solid rock of the planet itself. And that has some pretty profound long-term consequences.
Because all this constant stretching and relaxing, well, it isn't free. It creates friction. It dissipates energy.
and it leads to this slow but completely relentless transfer of energy inside the Earth-Moon system.
Okay, let's walk through this, because it's beautiful. First, the Earth spins way faster, once a day, than the Moon orbits, which takes about a month. So our planet's fast rotation drags those two tidal bulges slightly ahead of the Moon. Second, that leading bulge of water has its own gravity, and it pulls forward on the Moon, giving it a little energy boost. At the same time, the Moon pulls back on that bulge, creating a drag that ever so slightly slows the Earth's rotation. Third, that energy boost to the Moon pushes it into a higher and, funnily enough, slower orbit. And fourth, the grand result of all this is that our day is actually getting longer.
And we can actually measure this. We have reflectors on the Moon from the Apollo missions, and by shooting lasers at them, we know the Moon is spiraling away from us at about 3.8 centimeters every year. That's roughly the same speed your fingernails grow. It sounds like nothing, but over billions of years, it really adds up. And this whole thing is a two-way street. The Earth's much stronger gravity already did its work on the Moon ages ago, slowing its spin until it became tidally locked. Its rotation period now perfectly matches its orbital period, which is why we only ever see one side of it, the man in the Moon. And now the Moon is slowly returning the favor, locking us in that same gravitational hug.
And hey, if you want to see the true terrifying power of tidal forces, just look at Jupiter's moon Io. It's caught in this insane gravitational tug-of-war between giant Jupiter and its other large moons. Io is constantly being stretched and squeezed like a cosmic stress ball. All that tidal friction generates an unbelievable amount of heat, making it the most volcanically active body in the entire solar system. This isn't just a gentle nudge. This is a force that forges worlds.
So let's bring it all back home. Is Earth on a razor's edge? Well, the answer is no, but for reasons that are way more complex and interesting than we thought. Habitability isn't just a static address in space. It's a living, breathing, dynamic process. It's this delicate dance of gravity and tidal forces that sculpts a planet's day, its orbit, even its internal geology. A stable home in the universe is so much more than just being in a just right spot. Realizing how tides work revealed this whole hidden layer of physics that governs how worlds interact. And it just makes you wonder, as we look out into the cosmos for other Earths, what other fundamental forces, what other hidden interactions are we totally blind to right now that are silently shaping the fate of those distant worlds? What else is out there, just waiting for us to figure it out?